So what I'm going to talk about in this video is the fact that when we have forces between molecules, these forces are going to be due to their structures. It could be due to, are they sharing electrons or not? And so we have to use some of the things we already learned in previous chapters to figure out what forces are between molecules and then what properties do they have from that. So I gave you out these examples, so I'm going to work some of them with you so you could kind of see where I'm going with this. So the first set of questions you're going to see have to do with, again, polarity, because again, if a molecule is polar or nonpolar, you're going to see a different behavior between those molecules. So you will still have to know what the shape is to determine if that polarity, if it is polar or nonpolar. So I'm going to pause the video and I will show you each one of the shapes and if it's polar or nonpolar. So you could pause it and draw it yourself. So I've drawn each one of these. So H2S is a bench shape because it has two lone pairs. CCl4 is a tetrahedral. And then SO2 is a trigonal planar bent because you kind of have this double bond having resonance in that structure, and that lone pair is going to fill up one of the spaces around that central atom. So these would all be given at, let's say, 25 degrees Celsius solids. They are going to be classified as molecular solids because they have covalent bonds in them. But again, between solids and liquids, we're going to just take it as what temperature are you at? Are you at a liquid or a solid? So if you have a bent shape, that's going to make it polar. Tetrahedral is going to tend to be nonpolar unless there were different things attached. And trigonal planar bent, typical trigonal planar would not be polar, but because you have one lone pair and then bonds on one side, that would make it polar. So in terms of their forces between them, the nonpolar would have least amount of forces, and then the polar molecules would have the most, again, depending upon their polarity between the bonds. But all I'm asking you to do is to realize that that polarity is going to influence when I have a bunch of SO2 molecules together in that solid form. Are they going to be closely linked together? Is it going to be hard to break them apart? So that's where we're going to be using this idea for that. All right, so here is where we are going to see some organic molecules again. So I kind of want to review this because we talked about this at the beginning of the semester. And as I told you, there's a couple different organic molecules that tend to have some interesting intermolecular forces. And one in particular happens to be alcohols. So I'm going to help you draw each one of these and kind of show you how they are different in terms of their intermolecular forces. So CH3OH. So please remember, an OH group is going to be an alcohol group. It's going to be an alcohol group. So you have carbon as that first molecule. So attach 3 hydrogens to it.
May I have your attention?
So I have my 3 hydrogens and then my OH. Well, this is where organic chemists are kind of weird with how they do their functional groups. They typically just write OH. But for me to draw it with the lone pairs and everything, as you have learned it, might help you to kind of see that structure a little differently. So realize carbon is that central atom there. So this is a tetrahedral, but it's not symmetrical, okay? The OH, the oxygen is going to pull more on those electrons. So you're going to have some polarity with this particular molecule. And the other thing you're going to have is hydrogen is directly attached to oxygen. So you have something called hydrogen bonding. So please write down hydrogen bonding for anything that has an alcohol group. So again, the hydrogen's directly attached to the oxygen. I'll come back to this and draw this one again. But again, anytime you see an OH, that's going to be an alcohol. It's going to have hydrogen bonding. Amines have a nitrogen in them. You might think, oh, is that going to have something different in it because it has a nitrogen? Yes, it's going to have some hydrogen bonding as well. So CH3, CH2, again, is what we call a Molecular structure, it's much more of a condensed structure so that you kind of know, okay, this first carbon has 3 hydrogens on it. The next carbon has 2 hydrogens. So essentially I'm reading from left to right. And then I have a nitrogen on the end that has hydrogen and hydrogen. So again, nitrogen has a lone pair. That's why it does what it does, but organic chemists usually drop off that lone pair. Because hydrogen is directly attached to the nitrogen, this also has hydrogen bonding. And in terms of shape, you would have to do the 1-2 kind of situation to figure out what each shape is, depending upon what carbon you're at. And the nitrogen also would get a number because you would have to look at, okay, I got a bond here, a bond here, a bond here, and then a lone pair. So this would be a trigonal pyramidal, which is going to lend itself to a different shape. The shape is going to make that part of it polar. Okay, so that end will be polar. But the big force that you have here is hydrogen bonding, the hydrogen directly attached to the nitrogen. And then we have ethers. So ethers, what makes them unique is you have oxygen between 2 carbons. So again, I'm going to take 1 carbon, put an oxygen, and put another carbon. And then I'm going to have hydrogens on either end. So again, organic chemists typically do not put the lone pairs. I'm going to draw them here just so it doesn't make it feel weird. So again, this structure is going to have no hydrogen bonding. There is no direct hydrogen attached to that oxygen. Okay, so just by looking at their structure, you can look to see, okay, who has hydrogen bonding and who doesn't. So amines and alcohols are going to have that hydrogen bonding because the nitrogen is directly attached to the hydrogen and the O is directly attached to the hydrogen. So final question I want to look at is what is the strongest force if I just give you a list of chemicals? So iodine, I2, strontium chloride, this is a carbon-based molecule and this is an alcohol. So take a moment and see if you could draw their structure and then look at the dispersion forces. Do they have dispersion, dipole, or do they have hydrogen bonding? And do they have anything beyond that? So what is the strongest force in each one of them? So I'm going to pause the video and then come back. So I2 is a covalently bonded molecule. You would classify it more as a linear, non-polar. So the only thing that you forces-wise is the dispersion forces. So that is the lowest force. It is the force that all molecules have. So that is the strongest for I2. SrCl2 is an ionic compound. So you would say the strongest force is going to be Coulombic force. So does it have dispersion? Yes. Does it really have dipole? No, because it isn't covalent and it doesn't have hydrogen bonding. So you got to jump to what we call the intra. So within those bonds, the transfer of the electrons, and then you have the attractive force. That's the Coulombic force. That's going to be the strongest force that you have in that molecule. CH3CF3, because you have, again, this is a C1 and a C2, they're both tetrahedrals, but because the fluorines are going to pull more on those electrons, you have a polar molecule. So anytime you have a polar molecule, you have dipole would be your strongest. Does it have dispersion? Yes, but we are listing only the strongest force, And finally, our alcohol. Anytime you have an OH, that H is directly attached to that O, you have what we call hydrogen bonding, okay? So hydrogen bonding, again, is one of those concepts that I think gets misinterpreted. So I'm just going to draw the alcohol one for you. So the oxygen is going to pull more on the electrons than the hydrogen. So it's going to have a partial negative, and the hydrogen is going to have a partial positive. So when you have a neighboring alcohol, the O8 part of that molecule is then going to be drawn closer to that hydrogen end because it has a negative charge and the hydrogen is positive. So anytime you see hydrogen bonding, it's like a dotted line between the two molecules. So that's what we call the hydrogen bonding. So it's a little weirder to do it with alcohols or really big molecules. The one that you always see is water because it's such a small molecule. So it's much easier to draw hydrogen bonding with that. But realize because you have the oxygen pulling on the electrons more, you have a partial negative and a positive, which is going to make the neighboring molecule kind of organize itself from there. So those are some examples I just wanted to kind of give you a heads up on how to kind of combine what we learned with the covalent and ionic bonds and now deal it with forces.